Okay, you might have thought that you knew how to count already, but we're going to be dealing with some counting techniques. These work well into some probability events that we're going to look at soon. And we're going to talk about four different counting techniques that we'd find useful. The first of which is the least sophisticated, but maybe it's the best go-to. This will, in theory, always work, provided we're not trying to count how many lottery combinations there are in the big game, provided it's a fairly finite uh, number that we're looking for. For instance, this is a grounded out technique. There's a better way of solving the problem I'm about to illustrate for you. But let's say we have three people, and for convenience sake, we'll call them A, B, C, and D, and we are going to just choose two of those people to go to a movie with us, and we'd like to know how many different groups of two there are. And while there may be a more sophisticated technique, the grinded out technique, we could just start listing them. I could take A and B, I could take A and C, I could take A and D, I could take B and C, I could take B and D, or I could take C and D. So in that case, there are six possibilities. And that's just an example of grinding it out. And oftentimes that would be a last choice, particularly as the numbers get bigger. But sometimes we don't have a more sophisticated method than just listing these out. But other times, examples 2, 3, and 4 here, we may have some better examples. The first time I think I ever encountered fundamental counting principle, and a lot of my students share this same um, experience, was but what I would refer to as the closet problem, where we have perhaps two pair of pants and three shirts to choose our outfits from. And let's say that we have a pair of blue pants and a pair of green pants. So we go to the closet, and first we select pants. We can select blue or green. And then if we have three unique shirts, um, we can choose blue pants with our white shirt, blue pants with our blue shirt, or blue pants with our red shirt. Or we could select green pants with our white shirt, or green pants with our blue, or green pants with our red shirt. And we see that in this case, we have six possible outfits. And of course, we quickly discover that we can just multiply 2 times 3 and arrive at our six solutions. So if we're going to make some choices and then make choices and then even further make more choices, and we can just continue the progress of multiplying the number of choices along the way. So I have two choices of pants, three choices of shirts. I'm going to choose two, and I'm going to choose three. Very oftentimes when we use the word and, we can just substitute multiplication for and. So I'm not going to wear two pairs of pants or three shirts. That would not be such a great decision if I was going out, but I'm going to choose from two pair of pants and three shirts. That's a multiplication principle or fundamental counting principle, which we may classify as a closet problem. And the last two, you should by this point be familiar with the mechanics behind combinations and permutations. Both of these cases, very similar. We have to just determine whether ordering is important. For combinations and permutations, if we are choosing a group, and the group may just be one, if we're choosing a group from what is often a bigger group, but from a group, for instance, I have 23 students in class and I'm going to choose three of them to take to lunch with me, then we're dealing with either a combination or a permutation. What makes the difference is in combinations, the order does not matter. In permutations, the order does matter, as you're going to see with some examples. We're going to talk about how we go through those problems. So again, combinations, permutations are identifiable if we're choosing from a group. If, back to my lunch example, I choose 3 of my 24 students to take to lunch as it's phrased now, that is a combination problem, because if I choose A, B, and C to go to lunch, I've also chosen C, B, and A to go to lunch. The order didn't matter. However, if I phrase it this way, if I choose 3 of my 24 students to go to lunch, one of the students, I'm going to buy their lunch for them. The second student can ride along, and the third student I'm choosing because they're going to he or she's going to have to change the flat tire on my car. Now, if I choose you as part of ABC, there may still be a little trepidation there because the ordering matters. So A, B, and C would imply a different result than B, C, and A in that order. So that's the tricky part about combinations and permutations, is determining when is it implied that the order does in fact matter.